Progress.
Hello, everybody. Welcome to the February lunchtime seminar meeting of the Canadian Meteorological Oceanographic Society's Ottawa Centre. We're very pleased to welcome Dan Shan, assistant professor in the Department of Physics and Space Sciences of the Royal Military College, Kingston, as our speaker today. Dan is an expert on hydrodynamics of fjords, continental shelves, and inland lakes. And his work is sort of like "This Land Is" the song, "This Land Is My Land," from coast to coast to coast, Halifax to Kitimat Fjord to the Arctic. And his topic today is wind-driven coastal upwelling of Nova Scotia. And without further ado, I'm going to turn the floor over to Dan, and then we will have discussions by chat, driven by your chat messages afterwards. So, Dan, welcome.
Okay, thank you very much. And just do a mic check. Can you hear me well?
Yes, Dan.
Okay. Thanks for the introduction. So it's my pleasure to present at this seminar series. And the title of my talk is "Wind-driven coastal upwelling of Nova Scotia." So as you can see from this image, shows the sea surface temperature from the operational ocean forecast that shows ongoing upwelling events in July last year. So the focus of the area I'm going to focus on is Scotian Shelf, and some of you are quite familiar with this region. Some of you may not very familiar with this region. So let me give you a quick introduction. So this region is called the Scotian Shelf. It's bounded by Northeast Channel and Laurentian Channel. So this region here is Nova Scotia. What you see, the colored image, is sea surface temperature. The color bar shows from about 6 degrees to 28 degrees. So this is in July. As you can see, along the south shore of Nova Scotia, the temperature is quite low. It's about 8 degrees, so that is quite cold. This is due to the wind-driven coastal upwelling. So I will explain this coastal upwelling process in this presentation. So first of all, I want to acknowledge the contribution from my collaborators at Dalhousie, RMC, and Environmental Climate Change in Canada. So now let me try to move to the next slide. So at the beginning, I want to give you a quick overview of my research. So I'm a physical oceanographer who is specialized in numerical prediction of coastal shelf circulations. So here shows three my recent research projects, and one is in the East Coast in Halifax Harbor to study the small scale circulations using a high resolution model, AUV, and drifters. And the second project highlights the field shelf exchange in the Kitimat Fjord system in the west coast of Canada. So the last one is an interdisciplinary project that is in collaboration with biologists and to study the spawning ground larval production and transportation for two commercial fisheries species in the Great Lake Erie. So in today's presentation, I'm going to focus on another very interesting and challenging topic, that is wind-driven coastal upwelling on the Scotian Shelf. So first, I will introduce you the theory of the wind-driven coastal upwelling. And then I will look at in details the coastal upwelling events in the year 2012, and that is a year that we have a good set of observations. So we'll look at observed coastal upwelling, modeled coastal upwelling, and then I will present a few process study to look at some of the key processes and drivers. So, and then I will focus on the second part of the talk is to look at the trend in coastal upwelling over the past 20 years. And the last I will touch on the operational model predictions of the coastal upwelling in this region. So the coastal upwelling is tightly linked to the Ekman theory, and this is a basic question that we have observed before. The question is, why does surface water move in a different direction than the wind? So the question first reported by Nansen in the Fram expedition that is in 1893 to 96. So what he found is the ice drift produced by a given wind did not, according to the general opinion, follow the wind direction, but deviated 20 to 40 degrees to the right. So Nansen explained this deviation as an obvious consequence of the Earth's rotation. So Nansen suggested this topic to Ekman, and Ekman invited the problem mathematically and developed the Ekman theory in 1905. So what you saw on the left-hand side, this shows the classic Ekman spiral, and the vertical arrow T represents the wind direction, and the longest arrow shows the surface current that is pointing 25 degrees from the wind. So if we do a vertical integration from surface to a certain depth, then we have the night transport of the water in the direction 90 degrees from the wind to the right in the northern hemisphere. So I didn't include any equations. The Ekman theory for the steady state Ekman current is basically linked to the Earth's rotation, that is the Coriolis term balanced by the vertical mixing term. So now we have the basic Ekman theory, and we can explain the coastal upwelling phenomena. So the Ekman transport is at 90 degrees to the right of the wind direction on the northern hemisphere. So suppose, imagine this is the coast of California. If you have a north wind along the west coast, and that will cause the Ekman transport away from shore. But the water transported offshore must be replaced by water that is wells up. If you look at a sectional view, so this arrow represents Ekman transport, then you have a deep water moves up to replace the surface water. So typically the deeper water has a lower temperature, and this result a thin strip of low temperature adjacent to the coast. So this would be a signature of welling in the summer. So offshore the water is warmer, near shore the water is colder. So we could use that as a proxy to identify the ongoing upwelling events along the coast. So this water moves up from deeper layer to surface layer is also a major mechanism for transporting nutrients onto the shelf from deeper water. So this is a global map, give you a global perspective of the upwelling along the coast. So this process is of great ecologic importance. It's responsible to bring the nutrient-rich water to the surface. It's also sustaining productive fisheries and marine ecosystem worldwide. A different color represents various degree impact of upwelling process on different coasts. So what you immediately see is that nearly all the coasts at a global scale are all affected by this coastal upwelling process. So for the purple color, this shows that upwelling is very important. That is located in the west coast of North America, South America, and also in the west coast of Africa. So to show you an example, so this is a satellite image in this time of year, but in year 25, shows the upwelling of coast of Chile. So what you saw is a similar pattern that on the coast is relatively colder water, offshore you have relatively warmer water. And we could use this low temperature as a proxy for the upwelling process. So now I want to pause for a few seconds and asking you to try to draw the alongshore wind direction and Ekman transport as I have showed previously for the Ekman theory. So now the Ekman transport is away from shore, that is moved from shore to the open ocean. So although the Ekman theory was developed in the Northern Hemisphere, but it also can be applied to the Southern Hemisphere. In this case, the Ekman transport would be to the left of the alongshore wind direction, which means in this case, the wind was blowing from source to north direction that caused a offshore Ekman transport. So the coast upwelling theory developed can also be applied to the large lakes. So this is an example, shows the upwelling process in the Lake Ontario. So what you saw is at 2 years, same date in September, in year 2021, what we saw is relatively colder water along the north shore of the Lake Ontario. Again, if you apply the prevailing wind direction and Ekman transport, this time the wind is blowing from east to west. This time the wind is blowing from west to east, and then that caused Ekman transport to the south direction. So in the year 2022, and the cold water was actually situated in the south shore of the Lake Ontario. In this case, we would have the prevailing wind blowing in the opposite direction, that is from east to west, cause a right-hand 90-degree Ekman transport. So if you take a look at the upwelling process in the west coast and east coast of Canada, and what you saw is that there's a very important upwelling process in the west coast Canada, and also significant presence of upwelling in the east coast of Canada. Today, I'm going to focus on the upwelling process of Nova Scotia. This is the satellite image capture upwelling process in September year 2012. Again, you saw this low temperature along the coast. So understanding the spatial distribution of this cold water generated by upwelling is very important, and that can be used to answer a recreational question. For example, which places are best for swimming? In the ocean, typically you would look for a higher surface temperature. And we can also understand, answer the question of scientific questions. For example, what are the impact of cold water on fisheries, aquaculture industry, and coastal ecosystems? So the coast upwelling on Nova Scotia was actually first reported by H.E. in 1937. So this image this figure shows the coastal upwelling process happening in 1934 in the month of August. If you pay attention to the dashed line that shows the temperature contour based on few black dots, based on few surveyed stations. And the temperature along the coast is relatively cold, about 12 degrees. And in 1987, Petrie reported major upwelling events in this region. And again, what you saw is this relatively colder water in July 1984. The temperature is about 8 degrees. And also there's an instability development, shows the upwelling filaments on the Scotian shelf. So as we expected that this coastal upwelling is related to wind. If you look at the geostrophic wind from the sea level pressure in this region, here is Nova Scotia. This part is relatively high pressure, this part is relatively low pressure. So we would expect the geostrophic wind from southwest direction. So this is the observed wind at Halifax at the weather station, shows the climatological wind in the summer months, and it's indeed the wind mainly from south and west direction. So again, we can apply the Ekman theory that the Ekman transport in this case is to the south direction, and we would have a wind blowing from southwest and to northeast that generate the Ekman transport, causing this bluish cold upwelling water. So now let me dive into detail to look at the observed upwelling events in the year 2012, in which we have a good set of observations. So there's a meteorological marine buoy located out of Halifax Harbor, and that is capturing the sea surface temperature time series. So this is from January to December. As you can see, the temperature is relatively cold in March, relatively warm in August. And what we saw is there are large fluctuations in the summer months, typically in July, August, and September. So those large fluctuations of sea surface temperature is actually caused by the coastal upwelling processes. There's a major upwelling events happening by the end of August, and the temperature drop is nearly 8 degrees. So this is give us a temporal time series of the coastal upwelling, and there's a satellite image shows below that indicates the spatial distribution of temperatures during this time of year at early September. So we actually indeed observe cold water along the south shore of Nova Scotia. So here I also want to highlight that the satellite SST coverage is strongly affected by a cloud or the atmosphere condition. So what you saw in this part is actually affected by cloud, and we can only get a few good satellite image and to capture the upwelling process every year. Often the satellite image is affected by cloud. So next I will explore the relationship between wind and the change of temperature. So this is again the wind observed by the marine buoy, shows from July to October. And first I'm decompose this wind into two components. One is a longshore component, shows in red, and the other is blue, shows the crossshore component. So what I'm going to focus on is this alongshore component, shows in red. And in addition to the wind stress, and we look at the wind impulse. And wind impulse is a temporal integration of this wind stress. For this area, and this time t integration time is typically about 5 days. So if you look at the relationship between red and black curve, we saw that this is the two are tightly negative correlated. The negative SST anomaly peaks are coincident while with the positive wind impulse anomalies. And then we can further do a linear regression. So what we saw is that the upwelling process can actually be separated into two processes. One is the initial response period, and the correlation is quite high between the wind impulse anomaly and SST anomaly. That is shown by the solid red circle, and also color-coded by the gray bar. So after the initial response period, and the correlation between the wind impulse and SST anomaly are not very high. So this is due to that SST are also affected by other physical processes, for example, the surface heat flux, horizontal advection, and vertical mixing. So we cannot use the simple regression model from wind to predict the change of SST. And then we develop a more complex circulation modeling system to study the upwelling process. So this shows the model domain. So it's a nested setup. So you have a bigger model domain has a quarter resolution, and smaller model domain focusing on the central Scotian shelf. Here is Halifax with relatively higher resolution. So this animation shows the model results during the upwelling events at the end of August and beginning of September in 2012. Left shows sea surface temperature, right-hand side shows the sea surface salinity. As we can see, the model has a scale to capture the relatively colder water along the Nova Scotia, not only in South Shore, but also in Bay of Fundy and south tip of Nova Scotia. In the surface salinity, we saw relatively fresh water that originate from St. Lawrence River and that propagating as a buoyancy plume and affect the salinity and in turn Nova Scotia current on the Scotian shelf. Since there are 3 cold water mass along Nova Scotia, and then I did a very simple process study to look at the tidal mixing and wind-driven and wind effect on generating those cold surface waters in this region. So we have a run that's driven by all the forcings, a run that without wind forcing, a run without tidal forcing. How do we know that the tide at Halifax Harbor is about 2 meters, not very large, but in Bay of Fundy, it has the highest tide in the world, that is about 60-meter tidal range. So this shows the model results. On the left is the control run. Middle panel shows that no tides. Right panel shows no wind. So this clearly indicated if you look at the middle panel without tide, we don't have the cold water in Bay of Fundy and the southwest tip of Nova Scotia. This is indicating the cold water in Bay of Fundy and the southwest tip. It's due to the strong tidal mixing and the tide topographic interaction generated topographic upwelling. So it's only in the south shore of Nova Scotia, it turned off the wind and the water is relatively warm on the Scotian shelf and along the coast in comparison with the control run. This shows that only this region and the cold water is generated by the wind-driven coastal upwelling. So next, let's take a look at the model performance in capturing the coastal upwelling. First, we look at the SST time series. The red is the observation we have looked at before capturing by the marine buoy, and the blue color shows the model simulated temperature as we can see, the model is able to capture the seasonal cycle of the SST. The model is also able to capture the upwelling events in July, and also this upwelling events toward to the end of August. So that is the time series comparison. If we look at the comparison with the spatial pattern, the satellite observed SST. As I mentioned before, as you can see, often the satellite image affected by the cloud shows in the white region, and in other times we are able to get an idea that there's ongoing upwelling in the month of July, shows by this yellowish and greenish colder color along the coast. If you look at the model results, the model is able to capture those relatively cold water along the coast in this months. So if we look at the continuous SST, daily SST in this whole month, and we can see that the temporal evolution of upwelling plume associated with the wind stress. So this black arrow shows the wind stress. Remember that the alongshore wind is going to generate Ekman transport that in turn cause the cold water along the coast. So I have taken the snapshot, and at the early July toward to the end of July, this is illustrated three processes. So on the first row shows the onset of upwelling. Initially, the temperature is relatively uniform, and we saw alongshore upwelling favorable winds, and that generated colder water along the coast. And then there's a further development of upwelling. Particularly on this day, we have a very strong upwelling favorable wind from southwest that will increase the cold water area along the coast. So the bottom row shows the downwelling process, which is opposite to the upwelling. In this case, we have downwelling favorable wind. The wind is from northeast to southwest. That is going to generate Ekman transport toward to the coast, and that is push the warm water from offshore to the coastal region. After this downwelling process, we saw that the temperature will come back to relatively uniform again by the end of July. So next, if you take a look at the details along the coast, the cold temperature are actually not uniform. So in this two inlets, one is called Samaris Bay, the other is called Mahon Bay. The temperature is relatively warmer than the adjacent coast. So we did a correlation study. We correlate the temperature at the marine buoy with other regions on the shelf. So the two panels shows the correlation coefficient. One is in summer, the other is in the winter time. So first, if you take a look at the winter time, the correlation is relatively symmetric to the upstream and downstream. But in the summertime, the decorrelation distance is actually shorter to the southwest in the downstream direction than in the upstream direction in the summertime. So we speculate that this asymmetry may be due to this irregular coastline and also this shallow banks in this region. And this asymmetry could also have a considerable impact to the local circulation, local temperature, that in turn have a major impact to the larval transport, settlement, and abundance in the two inlets. And then we also conducted a process study to look at the topographic effects. So what we did is to have two special configuration of the model, and the middle one that we change the coastline to be a straight one. On the right-hand panel that we smoothed the shallow banks, that's called the temporal lange, we replaced by a smooth topography. On the far left, that it shows a control run with constant wind forcing. So this animation shows that under this constant upwelling wind forcing, what is the response of sea surface temperature in a 30-day period. So what immediately you saw that all the three cases have developed a cold upwelling plume. If you compare the middle panel with the left panel, we saw that the filaments at the coastal upwelling plume developed can freely propagate continuously along the straight line from north east to southwest. If you compare the far right to the left panel, and the presence of this irregular topography can actually influence the further offshore development of the filament by affecting the local circulation field. So this, again, the snapshot shows the model simulation for the three cases at day 3 to day 30, and then you can make a detailed comparison, as you can see clearly in the middle panel, that is the cold upwelling filament can freely propagate from northeast to southwest. And we didn't see the cases that in the other two cases on the left and on the right. So we further quantified the sea surface temperature response in these two inlets, and by calculating the area average SST in the St. Margaret's Bay and Mahone Bay. And that is shows by this three colored line shows the three cases. If you come, horizontal axis is time from day 0 to day 30. Again, we can separate the SST response into two categories. One is the initial response, the other is the continued response after 4 days. So immediately we saw the drastic differences from the red line in comparison with the blue and black line. So the red line, which is the straight line case, suggests that the irregular coastline is the main controlling factor to observe the relatively warmer temperature in the two inlets. If you compare the black and the blue curve, that is one the control run, the other with the shallow submarine bank smoothed, and we saw that the small scale shallow banks has less effect on the SST variation during the initial response period, but it plays an important role in the SST variation in the continuous response period. So by the end of 30 days, and what we saw that the three lines are actually converge to a relatively similar temperature. This indicates that when the upwelling plume is fully developed and the topographic effect is reduced toward to the end of this month-long simulations. So now let me give you a quick summary for part 1. So we initially look at the Ekman theory, and we look at the correlation between the wind impulse and the sea surface temperature. We found that a longshore wind impulse is a reliable predictor for the rapid sea surface temperature cooling during the initial or the onset of upwelling events. And we construct a circulation model to look at the complicated response of the upwelling plume after the onset. And we also studied that the irregular coastal line that the process study shows is responsible for the relatively warmer SST in the two downstream inlets. So that is look at the upwelling events in one particular year. So fortunately that we have this marine buoy located out of Halifax Harbor, and we have a total about 20 years record. And this allow us to look at the trend of upwelling process in this region. So that we know that it's possible that the frequency and intensity and duration of coastal upwelling may shift in a warming climate. So that understand its trend and predictability has become a question of vital importance. So in the second part, I'm going to show the result from the trend analysis. So first, let me explain the trend analysis process. So on the right-hand side shows the data in one particular year. In this case, I show the example in 2015. On top, we have the marine buoy observed time series. In the summertime, we saw the large fluctuations that is associated with upwelling process. And then we identify all those upwelling processes and construct a table and give each upwelling events a number recorded as a start time, end time, and the peak date, and also the associated temperature observed by the time series. And then we can calculate the duration and the change of temperature for each upwelling events. And we also use the satellite observed SST and also the glider observed section shows the temperature. What you saw in here is that in that particular year that the glider transect actually captured the cold upwelling front at this time period. What you saw in the gray shaded box shows a relatively colder temperature close to the coast. And we also, by doing this cross check, and we confirm each upwelling event from the marine buoy with the satellite observation and glider observations. So that is for particular year, and we can repeat this table for 20 years. And then we can derive upwelling matrices and to objectively describe a coastal upwelling trend in terms of frequency and duration. So we look at this 4 parameters: the number of events per year, average temperature drop, season start date relatively to July 1st, and percentage of upwelling days from July to October. So this 4 figures summarize those 4 upwelling matrices. The horizontal axis is time, about 20 years span from 2000 to 2020. And the vertical axis shows the 4 matrices. So what we saw, let me explain this 4 busy figure. And the first one shows the number of events per year. What we saw that initially the number of events per year is relatively small, about 1, and it has increased to about 4 over the past 20 years. And for the average change of temperature, we saw the average temperature drop during the upwelling season has steadily increased from about 4 degrees to greater than 8 degrees. And also, we look at the upwelling season start date, and this shows the start date shifted to be about 3 weeks earlier, and that's increased the overall season duration. So the last figure shows the percentage of upwelling days from July to October, and the percentage of upwelling days has increased from 13% in 2000 to greater than 50% in 27, and capped out at about 60% from 28 to 2020. So this funding, we compare this funding with other studies, and this is consistent with the result in other upwelling regions around the globe, suggesting the increase in overall temperature anomaly and season duration. So now we look at upwelling and upwelling trend, and naturally you would wonder, can we predict the coastal upwelling in our ocean forecast? So the last part of my presentation is to briefly introduce you the Canadian Operational Ocean Forecast System and show you the result of the forecasted upwelling events. So the Canadian Operational Ocean Forecast System developed by the Concepts Network. So Concept is the Canadian Operational Network for Coupled Environmental Prediction System. It's a collaboration between 3 federal departments, DFO, ECCC, and DND. So for the Operational Ocean Forecast System, so we have these 3 hierarchy systems that is called GOPS, REOPS, and COPS. So G stands for global, R is regional, C is coastal ice ocean prediction system. So this figure shows the concept coupled prediction system from global to coastal scale. So we have this global model, regional model, and coastal models. So what you saw is a smaller domain and higher resolution. The global model is at a 1/4 degree. The coastal model is at 1/36 degree. That is about 2 kilometers for the east coast. So the COPS model has highest resolution, about 2 kilometers. It's provide 48-hour hourly ice ocean forecast 4 times a day. So the operational forecast result are available at the data mart at this link, and the result can also be visualized at Ocean Navigator website. So this 2 image shows the 2 domains. One is for the west coast on the left, the other is for the east coast. So today I'm going to just show the result on the east coast. As you can see the results, the COPS can capture the energetic Gulf Stream region featuring the meanders, cold and warm core rings. But if you zoom in to the coastal region, so this shows upwelling events in the year of 2019. On the left-hand side is the observed upwelling events from MODIS satellite. On the right-hand side shows the prediction from the COPS model at the same date. So if you focus on the south shore of Nova Scotia, you saw this cold water band, and the model is able to capture the upwelling events quite well in terms of the temperature along the colder temperature along the coast, relatively warmer temperature in the 2 inlet, the Samaris Bay and Mahon Bay. But if you look at the upwelling filaments, and the upwelling filaments are slightly different from the operational model predictions. So this is due to the nonlinear nature of coastal upwelling filaments or coastal upwelling fronts, and that make their numerical prediction very challenging. So this is an ongoing work that in my group and in collaboration with the COPS development team at ECCC. So currently we are investigating the predictability of this nonlinear upwelling front and using the satellite observed SST, marine buoy, and also this COPS product for the year of 2019. So to the end of the talk, let me quickly summarize the main findings. So the first one is the alongshore wind impulse is a reliable predictor of the rapid sea surface temperature cooling. And also we using a process study shows the irregular coastline is responsible for the relatively warmer SST in the two downstream inlet. And the 20-year trend analysis reveals an increase in both upwelling temperature and anomaly, and also upwelling season duration over this 20-year period. So at the end of the talk, I want to give you these two take-home messages. So first one is that suppose you're going a summer vacation along the south shore of Nova Scotia, then the sea surface water temperature could be quite cold, about 8 degrees during a summer upwelling events. The second point is that if you look at the three images I listed on the right-hand side, so over the past 90 years, so we have made a remarkable progress in understanding and predicting the coastal upwelling. So the first study by H.E. in 1930s shows the cold water and based on only a few surveyed points. And in 1980s, that we are able to get detailed upwelling and upwelling filaments based on 2D satellite observed temperature field. So in the year today, so we're able to access operational ocean model predictions, and that provides us a three-dimensional field, temperature field from surface to bottom at 24/7. So I'm going to stop here, and I'm happy to answer your questions from the chat.
Thank you very much, Dan. We have already some questions streaming in, and I will proceed to pose those to you. The first one was from Don Conway, who asks about users of your predictions. Are local fishermen aware or interested in the work? It would seem very useful in identifying good fishing areas. And I might add, I have the same question for aquaculture users. So, are you?
Yeah, that's one of the question, the motivation question I posted in the earlier presentation. That is the scientific question we could answer. That is to look at the cold water distribution, particularly during the upwelling events, and so which region is colder, which region is warmer, and the local fishermen are definitely very interested to know, and also, of course, the aquaculture industry. I know there's a couple of aquaculture industries in the particularly in the south shore of Nova Scotia, and so right now from the current study, we can based on the wind, we can relatively accurate predict the ongoing upwelling events, but from the because the nonlinear upwelling front is still quite a challenge task to exactly pinpoint where the upwelling front is exactly located, because the front is where you have a sharp temperature gradient, and this side of the front could be quite warm, on the other side it would be quite cold. Yeah, so I think there's still a lot of work to be done to actually make more accurate predictions of upwelling front, and we have a very good skill to predict the upwelling cold water band, but the upwelling front is still quite challenging.
In this regard, are you limited by model resolution and computing power in dealing with these nonlinear filaments?
I think that could be potentially a one factor, and the other factor, contributing factor, we're still investigating is related to the stratification and also the Nova Scotia current along the coast, and to see whether those conditions will also have an impact on the development of the instabilities.
Okay. So the second question was from David Fissel. Another type of upwelling modification under irregular coastlines would be the presence of canyons. Could you use your method to study this type of upwelling, such as the Juan de Fuca Canyon, the Mackenzie Canyon, where some process studies have previously been conducted?
That's a great question, David. And it's unfortunate I cannot see you, see you in camera. So the answer is yes, and you could use this type of process study, and by potentially make different configurations of the bathymetry of the canyon, and then to study the impact of different local topography on the circulation, and in turn on the upwelling processes.
And we have just a congratulations on a great educational presentation by Helen Joseph to you. Yes, I wondered, I think that we now have one more question. In all my visits to Southwest Nova Scotia over many years, we were always told that the Labrador Current was responsible for the cold beach water. How did you integrate this in your work? How is the Labrador Current involved here?
Image. So this figure cut it off. So there's a lot of outdoor current that goes around the Grand Banks, that in turn will influence the circulation on this slope water. So there's so this is Gulf Stream. There's interaction of the Gulf Stream with outdoor current, and that will in turn affect the eddies and the slope water front. And the impact of the slope water would affect the exchange between the shelf and the slope water, that will in turn to change the water mass property on the shelf, that potentially would impact the coastal upwelling processes on the summertime.
And I take it that this Labrador Current is underlying the surface, which is, if you have a little wind, gets warm relatively fast in the hot summer due to the solar heating. But as soon as you have upwelling, it brings the Labrador Current up. Is that right? This shallow current.
So I would see that the Labrador Current and the Gulf Stream on a basin scale, so it's on a larger scale. So the coastal upwelling I was focusing on today is on the coastal scale. So of course the large scale will drive the processes on the shelf in the coastal scale, but more regional or more locally, that the coastal upwelling may be affected by another current that is originate from the St. Lawrence River and of the Cable Strait, that is the Nova Scotia current that is flowing in this direction. So that will in turn more directly impact the coastal upwelling process. But of course, the large-scale interaction of the Gulf Stream and Labrador Current will indirectly affect the water mass property on the Scotian Shelf, and also the large-scale atmospheric circulation, and that in turn will have different wind condition, and that is the direct driver of the coastal upwelling on the shelf. So I know that this sounds
So
like less direct than the Ekman theory. Is more complicated and coupled atmosphere and ocean system.
Yeah. And so the Labrador Current isn't just the whole answer. It's you have the Gulf of St. Lawrence currents playing a role in infection. Question from Bob Jones. Can surface water heating in midsummer offset the upwelling in some situations of onshore winds where warm waters are blown towards the shore?
So I think the answer is yes, Bob, that if you have a very strong summer heating, then the water at the surface is warmer, then the surface water is warmer, that in turn will enhance the stratification. And if you have a strong stratification, then the wind will do more work to bring the colder water from deeper region to surface, and that could potentially suppress the upwelling process. So that is another factor that affects the upwelling process, is the vertical stratification or the density of the water. So a hotter water will corresponding to a lower density.
So shifting gears here, we have a question from John Stone on what are the potential effects on the carbon cycle of the...
That is a good question, John. But I'm not an expert in biogeochemistry, but I can speculate that as I presented in the presentation, that we look at the frequency, duration, and intensity of the upwelling process will change from year to year, and this upwelling will bring nutrients from deep water to surface that in turn will not only affected by the temperature that I was focusing on today, but also affected the biogeochemical cycle that will in turn have an impact on the carbon cycle.
So just to follow up, the trends that you're observing in the buoy from Halifax Harbor were such that you saw event frequency increase over the 20 years of 1 to 4, and a change in temperature from in the upwelling from -4 to -8. Is that correct?
Yes.
And so that certainly would give people living in the area the opposite impression about global warming, right?
Yeah, so that is one of the kind of counterintuitive results from this trend analysis, and often we would wondering that the global warming will increase the temperature on the shelf, but if for some reason, and I think that is still need further study, that the whole atmospheric circulation would enhance this southwest wind in the summertime, and that potentially could be a strong driver that will in turn will increase the upwelling frequency and the intensity along the coastal region, and that will in turn decrease the temperature, decrease the average temperature in this region in the summertime, and it's a counterintuitive impression in comparison with the global warming.
Well, Dan, I think it's time to stop the discussion now and to thank you very much for, as Helen noted, a very educational talk as well as a solid science talk that relates to everyday questions and experiences, and certainly to very important users such as the fishing community and the aquaculture community and the people living along the eastern coast. So thank you very much for that. I will remind people in closing that our next seminar scheduled for March will be given by Igor Skwarets, and it will be on how small craft can fill gaps in global coastal observations. So continuing on with the ocean science theme, and Igor is coming from RBR company, an oceanography company based in Ottawa, and also Sailing for Science theme that he is spearheading. So it'll be good to hear from him on the 23rd of March. So I would like to close by again thanking Dan and thanking all of you for attending, and wishing you a good spring. Thank you.
Thank you very much. Have a great day, everyone.